Hi, Astronomy. Mr. Janowski here. So, this is the first part of the slides for the last chapter of Astronomy for the year. And this last chapter is a double chapter. So, this is really chapters 14 and 15 from your textbook. So, this is going to deal with stellar evolution and stellar remnants. Also, the births, lives, and deaths. So, that'll be the stellar evolution. And the corpses of stars. That'll be the remnants. So, I find this stuff very interesting, and I'm hoping you will too. So let's get started. So here's the title: Stellar Evolution and Stellar Remnants, the Births, Lives, Deaths, and Corpses of Stars, chapters 14 and 15. So I'm going to quickly preview all the stuff we're going to learn. So back in chapter 12, we learned that gravity is trying to crush the sun, and pressure from nuclear fusion is trying to blow the sun apart, and all stars live this way. So what does it mean for a star to live? We're going to say that a star is living, a star is alive, when it's fusing smaller elements, lighter elements into heavier elements in its core. That's what it means for a star to be alive. And once that stops, the star is dead. So, yeah, this is the whole thing. Hydrostatic equilibrium. Yeah, gravity trying to crush the sun, pressure trying to blow it apart. The pressure comes from the high temperature in the star's core. That's the nuclear fusion going on in the core. All this stuff goes on, and then eventually the star is going to run out of fuel. It's going to turn out that low mass stars, which are stars that have between 0.1 and 8 times the mass of the sun, so the sun is a low mass star, their corpses will end up being white dwarfs. And the higher mass stars, so stars that have masses more than 8 times the mass of the sun when they're alive, will end up either as a neutron star or a black hole. So we're going to see why black holes happen in this chapter. So yeah, gravity trying to crush it, pressure from nuclear fusion trying to blow it apart. This is what the star is doing while it is alive. So, no, actually, this is what I just said in the last one. Yeah, so eventually they'll die, and low mass stars will become white dwarfs, and high mass stars will become either neutron stars or black holes. So this is one thing I want you to take from this. Very important idea in this chapter. Even though the high mass stars, they have higher mass, they have more fuel, so it seems like they have more things to fuse, so they should probably be doing it longer, but that's not the way it works out. High mass stars are going to die much more quickly than low mass stars because the high mass stars are going to use their fuel at a much higher rate. So even though the low mass stars have less fuel, they're going to go through it much more slowly, and the low mass stars are going to end up living much longer. So a low mass star like the sun will live for approximately 10 billion years. The highest low mass stars, the ones that are about 8 times the mass of the sun, they'll live for about 1 billion years. And the lowest of the low mass stars, 0.1 times the mass of the sun, they go through their fuel so slowly that they can actually live for like 1 trillion years. And why aren't there lower mass stars than that? Well, if they have less mass than that, then they never actually really start to be stars. Those are what are called brown dwarfs. They're kind of failed stars. They're like kind of like big planets. So think of a big Jupiter, but not enough mass to squeeze the whole thing together to start fusion to begin with. So yeah, that's a brown dwarf. But I digress. So another important idea: gravity is the thing that drives stellar evolution. Gravity, remember the 4 forces, the 4 fundamental forces in the universe: the strong and weak nuclear forces, the electromagnetic force, and gravity. Gravity being the weakest of all the forces by far. It's still what's going to drive stellar evolution. So what does gravity do? Well, it makes apples fall from trees. So yeah, here's a nice artistic rendering of Isaac Newton sitting under an apple tree, and an apple has fallen. It also makes the moon go around the Earth. So Newton's watching the moon out during the day. Remember back in the earlier chapters? Yeah, that happens. The moon's out during the day. It's actually out during the day half the time. Gravity also makes the Earth go around the sun. Gravity also makes the sun go around the supermassive black hole in the center of the Milky Way, and it makes the Milky Way go around the other galaxies in the local group and all that stuff. And it also drives stellar evolution. So yeah, gravity is going to be a big part in this chapter. So again, here's this idea. Low mass stars are going to live and die differently than high mass stars, and low mass stars are going to live and die. They're going to live much longer than the high mass stars. So I'll go through this in more detail in later stars, but these are the two kind of life cycles of stars. So here's a video from Phil Plait. I'll put a link to this in the description. I'd recommend watching this. So how does a star begin? So we're not even at the living star yet. The star is going to start off as an interstellar cloud, like between stellar stars. So just a cloud between the stars. There's the big cloud out in space. It is going to be tenuous, meaning thin, so not very dense, cold, dark mass of gas drifting around the galaxy. So yeah, you just have this giant cloud of gas, and then there's usually something that kind of gets the whole process going. So what is going to cause this cloud of gas to collapse and start to form a star? It may collide with another cloud of gas that's also just drifting through space, or you may have an explosion from a nearby star that sends kind of shock waves through this, this cloud of gas, compresses it in different places, and gets the whole thing going. But yeah, we're going to start out on our diagram. We're up here. So you've got this giant cloud of gas. It's a few light years across. And it's going to start to collapse. And gravity, of course, is going to be the thing that makes it collapse. So if we're talking about the sun, this collapse takes a few million years, which sounds like a very long time. But in terms of the lives and deaths of stars, that is a tiny, tiny fraction of the life of a star. So I'm going to keep putting the, a few million years. So 20 million years is going to be 0.020 billion years. I'm going to keep putting the times in terms of billions of years. So I did that for a while, and then eventually it becomes this thing called a protostar. So it's starting to collapse, form this little disk with these jets. We'll get to the jets later. And at the center of this collapsing cloud is, the densest kind of clump. This is the clump that will eventually be the sun. So it's not actually fusing anything in its. It's not doing fusion, in its core, at all at this point. So it's not actually a star. It's glowing because it's hot, but it's not actually doing fusion. So it's not really a living star yet. So at this point, gravity just keeps doing its thing. It keeps drawing more and more mass into, this little protostar, and it starts getting smaller and denser and hotter. And then eventually, it gets so dense and hot that it's now hot enough in the core of this thing to start doing nuclear fusion. So it's going to start doing this proton-proton chain that we learned back in chapter 12 when we learned about the sun. And once it starts doing this, one is we now have a living star. This is the beginning of the sun's lifetime. And now we have pressure pushing outwards from this nuclear fusion, and this is going to counteract the gravity. And this is also going to shut down all of the collapsing, because gravity was trying to pull everything together, and gravity was basically, winning. It was doing that. But now that we have this fusion creating this heat and this outward pressure, it's going to stop that. So no more things are going to collapse onto the sun at this point. So at this point, interstellar gas cloud, protostar, and now we have the sun where we are today. So the sun has joined the main sequence. So yeah, this is going to be the largest part of the sun's life, will be its main sequence star. And we're kind of right in the middle of that right now. So, our best estimate is the sun is about 4.5 billion years old. It's going to live on the main sequence for about another 5.5 billion years. So this is where we are right now. And now we're going to look into the future and see what's going to happen after that. So after about, another 5.5 billion years, after about 10 billion years of being a main sequence star, the sun is going to run out of hydrogen fuel that it can fuse in its core. So without hydrogen that it can fuse, at this point the core is only hot enough to fuse hydrogen. Without hydrogen to fuse, gravity starts to win. It starts to crush the core down smaller and smaller. So now the core is getting smaller. It's also getting hotter, and it's a couple of weird kind of seemingly contradictory things are happening here. So the sun, the core is going to shrink and get hotter and hotter. That heat is going to travel to the outer layers of the sun, and it's going to push them outwards. So the outer layers are going to get bigger and bigger. So core getting smaller and hotter, and the heat that it's generating is going to push out on the outer layers. So the sun is going to become a red giant. So core is now smaller, but the outer layers are way bigger. So the sun has entered its red giant stage, its first red giant stage, in fact. So it'll be in this red giant stage for about 1 billion years. So it was a main sequence star, for 10 billion years. So if we look over here at the graph, the sun is here for about 10 billion years, and then it becomes a red giant for about 1 billion years. So it shoots up to here on the HR diagram. So eventually, the sun's core is going to get so hot and dense that it is now hot enough to start fusing the helium that's in the core. So hydrogen fuses at a lower temperature than helium does. So right now, the core of the sun is hot enough right now, in the year 2020, the core of the sun is hot enough to fuse hydrogen, but it's not nearly hot enough to fuse helium. But 5.5 billion years from now, and another billion on top of that, the core will have become so hot that it can start to fuse helium. So it's going to start turning atomic element number 2 into the higher things, not just 3 and 4, but also up to 6 carbon. So it gets a little complicated. So now the core is hot enough, and most of the heat that's being generated in the core kind of stays in the core, which means less is getting to the outer layers, so the outer layers start to contract. So the sun is actually going to start to get smaller. So it stops being a red giant, and it starts to be a yellow giant. So it's, smaller than it was when it was the red giant, but the outer layers are also hotter, so now it's yellow instead of red. So on the HR diagram, main sequence, red giant, and then it'll kind of drift over here a little bit is where your yellow giant would be. Because it's smaller and hotter. It's a yellow giant. And it's going to stay in this yellow giant stage until it runs out of helium to fuse. So this doesn't take as long as the last stage. The last stage took 1 billion years. This only takes 1/10 of 1 billion years. So only 100 million years. And once it runs out of that, it becomes a red giant again. So now we're at this stage. So the second red giant stage doesn't last nearly as long. So a mere 50 million years, 0.050 billion years. So at this stage, there's not enough. The sun has gotten so big. The sun isn't anymore. It's much bigger than it was than it is right now in 2020. But it's not any more massive. In fact, it's far less massive at this point, which means it's so big that the gravity of the sun is not holding the outer layers nearly as well because there's less mass to do so. So the outer layers are going to just kind of drift apart, and they're going to drift away, and they're going to become what's called a planetary nebula. So here's the planetary nebula. You've got the core of the sun, more on that in a second, and the outer layers are just drifting away from the sun. Now, in the Crash Course Astronomy video, Phil Plait kind of says that the sun doesn't become a planetary nebula, but that's sort of debatable. I think he's just using kind of too strict a definition of a planetary nebula. So basically, I think the sun will become a fairly dinky, kind of wimpy planetary nebula, but I believe that it will become a planetary nebula because you'll have the core of the sun in the middle, and the layers that were the outside of the sun are just now drifting away. So it's called a planetary nebula, which is actually a terrible name for this thing. More on that in future slides. So planetary nebula. So after a mere 10,000 years, this last stage was a mere 50 million years, 0.050 billion years. This next stage will be only 10,000 years, 0.00001 billion years. The planetary nebula has just drifted completely away. So all that stuff has dispersed. So kind of poetically, perhaps, that the stuff that was in the sun, it's now just a big cloud of gas. So what happens? Some of this cloud of gas will be an interstellar gas cloud, and then maybe it will collide with another gas cloud, and the whole thing will start over. So, the stuff that is our sun now in, 7 or 8 billion years after the sun has died will drift apart and it will recycle. It will become another star, which is pretty cool. So, yeah. So now on this, we're going up to here. The layers have drifted out to that. So at this point, the only thing that's left is what was the core of the sun. So the sun's naked core, meaning it just doesn't have its outer layers anymore, is now the white dwarf. So the white dwarf is the corpse of the sun. It's not a living star because it's not doing fusion anymore. So this is the corpse of the sun. It's white because it is extremely hot. Now, the only reason that it is extremely hot is that it was extremely hot when it was doing fusion, and it's going to take a long time for all of that heat to go away. So now, we have just the dead core of the sun. So this is only about 1/100th the size that the sun is now. So this dead core is about the size that the Earth is. So it's only 1/100th the sun's radius, which means it's only 1/1 millionth of the sun's current volume. However, it still has about half of the sun's current mass. So it's way smaller in terms of radius and way, way, way smaller in terms of volume. But in terms of mass, it's only a little bit smaller. It's only about half as small. So this white dwarf phase is going to last for a very long time. This white dwarf, it's the core of the sun. It was extremely hot, so it's going to stay extremely hot for a very long time, perhaps more than 1,000 billion years, perhaps more than 1,000,000,000,000 years. So the universe is only about 14 billion years old, and this white dwarf corpse of the sun is going to be a white dwarf for 1,000 billion years. So 1,000 is far greater than 14. This is many times the current age of the universe. So eventually it will just radiate away all of that heat. It's going to take a long time because it was so hot and it's so extremely dense that there's a lot of heat there. But it will eventually radiate away all that heat. And then it becomes what is called a black dwarf. So the thing about this is, what our theories predict. We have never found a black dwarf because we don't believe any black dwarfs currently exist. The universe is far too young for this to have ever actually played its way all the way through. We found lots of white dwarfs, but white dwarfs just happen at the end of a low mass star's life. You've got to wait far longer than the current age of the universe for that white dwarf to lose all of its heat and become a black dwarf. So at the bottom, no white dwarf star has ever died in this way. So the already dead white dwarf has never died further by losing all of its heat and becoming just a black dwarf. Yet, we think this will eventually happen. So here's the whole timeline. All the different stages, and the right-hand column is how long each of those stages last in terms of billions of years. So we go interstellar gas cloud for a mere 0.02 billion years, and then a protostar for a mere 0.001, and then we enter the longest stage of the sun's life. It will be a main sequence star for about 10 billion years. And then, after it runs out of hydrogen to fuse in its core, it becomes a red giant star for the first time. This will last 1 billion years, so still a fairly long amount of time. And then for 1/10 of a billion years, it'll be a yellow giant. And then for 1/20th of a billion years, it'll be a red giant again, so not very long on this scale of things. And then it will just briefly be a planetary nebula. And then it will, for a very long time, once it's dead, be a white dwarf. So here's the same idea again, just with, the different timelines all played out here just to get you a sense of the scale. So the big yellow bar, this is the sun's main sequence life. This is its first red giant part. And all of the other stages, they don't last very long. So you can see how they're very small slivers on this. And this is the whole thing. I'll go over this quickly here. This is the whole thing being played out on. Do you recognize what kind of diagram this is? This is actually an HR diagram. You have luminosity up here and surface temperature down here. So from the very beginning, a protostar, I feel like this line is way too high because a protostar is not going to be all that bright. So it should actually probably be way down here. But yeah, the protostar, interstellar gas cloud, which puts out practically no light, and then it's a protostar, and then it joins the main sequence. And even though the main sequence on this is just this tiny little section, time-wise, this is the longest part of the sun's life. And then all the other things happen after that. And then it's very briefly a planetary nebula, and then it's a white dwarf for a long time. So yeah, from here to here to here, back to here briefly, and then planetary nebula and white dwarf. It'll shoot down to here. So to review, what lives longer, a low mass star or a high mass star? Low mass stars, being stars that have less than 8 times the mass of the sun, live much longer than high mass stars. So these things can live for billions of years. High mass stars might only live 1,000th as long as that, because high mass stars go through their fuel so much quicker. Now, which of the 4 fundamental forces drives stellar evolution? It is the weakest force by far. It is gravity. So yeah, this builds all the big things in the universe, including stars, and it guides how long the star is going to live and how it's going to live and how it's going to die. So what will the sun spend most of its life as? The sun will spend most of its life as a main sequence star. Then after its life, it's going to be dead for far longer than it was alive. What kind of corpse is the sun going to leave behind? The sun, being a low mass star, once it dies, is going to be a white dwarf. And it'll be a white dwarf for many times the current age of the universe. So that that'll be its death. That will last much longer than its life will. The sun will end up as a white dwarf. And then after about 1 trillion years, it will cool off, so it's not putting out any appreciable light. And then it is a black dwarf. But again, that hasn't happened yet. So that's it for the first part of the slides. Hopefully you found that interesting.